everybody! Today we are going to learn about calculus in 5 minutes. Calculus answers two main questions. It helps us find the slope of a tangent line to a curve and the area under a curve. That means that's a tangent line. We can find the slope of that using calculus. To understand derivatives, you have to understand one very important concept, and that is limits. Bam! You understand limits. Happy? The average rate of change would be the total distance divided by the total change in time. This is the average velocity. The instantaneous velocity, now let's represent this graphically. Let's say we're going from 1 to 7. Now to find the average, we're just going to take the slope of this line, which is called the secant line. The slope of this line would be 4 firsts. Easy enough to understand. Now, on the instantaneous rate of change. Here's point C. How do we find the instantaneous rate of change, you ask? We can't take the slope of anything here, but we can. Let's start taking slopes of secants, because as the interval over which we're taking the average rate of change gets smaller and smaller and smaller, we're getting closer to the instantaneous rate of change. So if we go from A to B, that's pretty far from our instant. But if we go from C to B, it's getting closer. If we go from this point to C, we're getting closer still. So, if this function is f of t, the initial a happens at t sub 1 and b happens at t sub 2, we can represent the average rate of change of the position as f of t sub 2 minus f of t sub 1 over t sub 2 minus t sub 1, because that is just the slope made fancy so that we can apply it more liberally later on, right? Because it's change in the y values over the change in x values, yes? In this case, change in x values over the change in t values, right? Right. So, now, we're doing the instantaneous, and if this is the general form for the slope of the secant, and we're getting t sub 1 is getting closer to t sub 2, this is becoming more and more like this. Getting closer and closer to being the same slope as the tangent line, you see? So the limit as t sub 2 approaches t sub 1 of the slope of the secant will be the slope of the tangent. This is the very beginning of the derivative. Now, let's write this in general form. Instead of f of t, we're going to use f of x. Instead of t, we're going to be using x. So, the average rate of change formula is basically your slope formula. And the instantaneous rate of change formula is the limit as x sub 2 approaches x sub 1. So the instantaneous rate of change formula is the limit as x sub 2 approaches x sub 1 of the slope formula. That means as this distance between a and b, x sub 1 and x sub 2, approaches 0. Now, remember that concept is coming back. I'm glad you understand those concepts. We're moving on to the actual definition of the derivative, which is the limit as h approaches 0 of f of x plus h minus f of x over h. The derivative is actually going to give you the slope of the tangent line at x. Also, that's going to be the instantaneous rate of change of the curve at x. But you're wondering, Liz, how did we get there from the instantaneous rate of change? I'm confused and lost and scared and terrified. Well, it's actually quite lovely. I love it. I love it. Okay, remember this? Yes. Remember how we mentioned a few seconds ago that x sub 2 minus x sub 1 would equal delta x, right? And let's call delta x h. So as x sub 2 approaches x sub 1, won't h approach 0? Huh? Yeah. Because x sub 2 is getting so much closer to x sub 1 that if you subtract them, it's going to be basically 0. X sub 2 equals x sub 1 plus delta x, which equals x sub 1 plus h, right? Okay, cool. Now let's rewrite this guy here. Now doesn't that look really similar to that? Huh? So there's your definition of derivative. Cool, huh? And there are a bunch of other ways to write derivative and a bunch of differentiation techniques. See ya!